Okay, today we're going to be looking at the next section, how we apply what we've been learning about radicals to a practical element in maths, which is the Pythagorean theorem. And Pythagoras discovered that when you have a right triangle, if you find the squares of the two shorter sides, they will equal, when added together, the square on the longer side, which is called the hypotenuse. So that's Pythagoras' theorem there, with a triangle ABC, where C is the hypotenuse, a squared plus b squared equals c squared. Now, we can do some very simple examples. We can do a very traditional Pythagorean right triangle, which is like that, and the units here, we could say, well, this is 3, and this is 5, and we're not sure what this one is, we'll call that one b. And if we put these elements into our Pythagorean theorem, we get that 3 squared plus b squared equals 5 squared. Let's simplify that. 9 plus b squared equals 25. Let's subtract, isolate b squared equals 16, and then b equals the square root of 16, which equals 4. Okay, so this is the very traditional, famous 3, 4, 5 triangle, and this is how we use radicals and use square roots to solve problems using Pythagoras. Let's look at another example. So we've got a triangle like this. Don't know the short side, but we have the other two. Again, we can put our values into the Pythagorean theorem. We get a squared plus 6 squared equals 7 squared. We simplify a squared plus 36 equals 49. We can balance our equation to isolate a squared. 49 minus 36 is 13. And we then say that a equals the square root of 13. Okay? So sometimes when we simplify this we get an integer, but more often we don't. And we're going to write them in this radical form. So what I'd like us to do is to go to page 740 in the textbooks, and we're going to do questions 3 through 14. I'm just going to include them here. Okay. All right. Pause the recording, work through as many of these as you feel you need to, and check your solutions. Okay. Now, often our problems are not so simple. Quite often we are faced with problems including variables, including unknowns, but we still have to use Pythagoras. So let's look at this particular one here. We have a right triangle with the side of x plus 2, x, and the hypotenuse is root 10. We're going to still use the Pythagorean theorem, which tells us that a squared plus b squared equals c squared, and in this case the side a is x plus 2, so x plus 2 squared plus b squared, which is x squared, equals c squared, square root of 10 squared. Now we're going to simplify each of these components. We'll start off with x plus 2 squared. X plus 2 squared, when we multiply out the brackets, we get x squared plus 4x plus 4. We then add the x squared. The square root of 10 squared is 10. let's tidy things up on the left-hand side. 2x squared plus 4x plus 4 equals 10. We can simplify that. And plus 4x minus 6 equals 0. What we've done here is we have taken the value on the right-hand side and moved it across. We've subtracted 10 from both sides. We now have a quadratic equation written in the correct form. This can actually be simplified. Every element can be divided by 2, so let's do that. So x squared plus 2x minus 3 equals 0. We've just divided by 2. And this looks like a factorable quadratic equation. So let's try that. So this is going to give us, now the p plus q is going to add up to 2 and multiply to negative 3. So I think that's going to be plus 3 and minus 1. So our values, x will either be negative 3 or 1. Now if we look at the context of the question, we've got a triangle who has a side of length x. Now there is no way that this can possibly be a negative. The concept of a negative distance is meaningless. So we can decide straight away that the negative value has no meaning, so x must equal 1 in this case. So the sides here, x is 1, x plus 2 will give us 3. So our triangle has a side of 3, 1 and root 10. All right. Okay, so let's work through those questions 17 through 19 on the same page. I'm just going to include them below. There they are. Work through those using the same techniques. Great. Now, we don't always get problems in such a neat format. Many of our problems are not going to be written down in such a neat way. They are going to be very wordy sometimes. So let's look at a particular example. So there we go. In this case, the best thing to do is to actually just draw this out. So let's try and draw an image of what they're telling us. A right triangle. So we start with a right triangle. Has one leg that is 3 inches longer than the other leg. Okay, so the longer leg is 3 plus the shorter leg. We don't know what the shorter leg is. We'll call it x. So the longer leg is 3 plus x. The length of the hypotenuse is 15 inches. 15 inches goes there. Find the unknown lengths. This seems to be quite straightforward. We'll use the Pythagorean theorem. So 3 plus x squared plus x squared equals 15 squared. Let's simplify that. This is going to give us 9 plus 6x plus x squared plus x squared again equals 15 squared. Let's simplify. 2x squared plus 6x plus 9 equals, let's work out what 15 squared is. I think it's 225. Let's balance that across. We'll move that to the other side by subtraction. X squared plus 6x minus 225 minus 9 is 216 equals 0. If we simplify this, we can divide by 2. And then we can factorize. Okay. And therefore x equals negative 12 or 9. Quite clearly, the negative 12 is extraneous, so x equals 9. And in this case, the lengths of our sides would be 3 plus 9, which is 12, 9, and 15. Okay. Okay. The problems we're going to do now are further down the page, at questions 20 through 22, which I shall include here. Alright, so pause it at this point and work through the problems. Okay, what we're going to look at now is what is known as the converse of Pythagorean theorem. And essentially the converse of the theorem is the theorem stated in a different way, but with the logic reversed. And the converse of the converse of the Pythagorean theorem states that if you have a triangle of sides A, B and C, where a squared plus b squared equals c squared, then the angle between A and B is a right angle, and it's a right triangle. Okay, so the logic is reversed. We started by assuming that the triangle was right and looking at the relationship between the sides. We're now reversing that, and we look at the relationship between the sides and then make the deduction that the triangle has a right angle in it. Okay, so some specific examples will be here. Let's do the first one as an example. So we have, it says tell whether the triangle is a right triangle. We've got the triangle 2, 3 and 4. If we look at our problem, we can see that the largest size, this is assumed to be the hypotenuse. The hypotenuse is always going to be the longest side. So the relationship in question 23, it's assumed that 2 squared plus 3 squared equals 4 squared. That is the question we are trying to answer. And let's answer that. 2 squared is 4 plus 9 equals 16, and that is clearly not true. 13 does not equal 16. So, for question 23, this is not a right triangle. Okay? So, complete the rest of these problems, and we'll come back and do some of the problem-solving questions in a few minutes. Right. Okay, I think we'll just start with one of the word problems. There's quite a few here, but let's just start with a simple one here, and we'll answer this. So we've got a structure, dampers built into the structure, yada yada yada. Okay, what is the length of each damper? Round your answer to the nearest foot. And you can see that the shape created by this support structure gives us a right triangle. The implication is that there is a right angle here. So if we apply this to Pythagoras, let's just sketch what we've got. We have a right triangle with a height of 12 and a length of 10, and we do not know, in this case, the hypotenuse. So our equation becomes 12 squared plus 10 squared equals c squared. So that's 144 plus 100 equals c squared. That's 244 equals c squared. C equals the square root of 244. And it says that we have to round our answer so we do not want a radical. Let's calculate that. The square root of 244 is 15.62. 15.62. It says to the nearest foot, so rounded, c equals 16 feet. Okay, quite an inaccurate answer, I would say. I would not like to round to such a degree, but anyway. Please continue with the rest of the word problems, specifically if we can look at questions 33 through 36, and there's the challenge question 32, which is also quite interesting. Okay.